Hey guys, welcome back to Business Statistics. Today we're going to be covering Chapter 4, Probability. Just a note of caution, Chapter 4 is definitely where the material gets a little bit harder. So I would say um, spend more time on this chapter than you would. I might be kind of giving you guys a little bit of extra time on this chapter. Like maybe we'll take a week and a half or something. But yeah, this chapter is going to require a lot more thought than 1, 2, and 3 did, and there's some concepts that are difficult to pick up, and a lot of the problems that we're going to look at are going to hinge on wording and your attempts to kind of analyze kind of what a question is asking, and so you're going to see that chapter 4 is a little bit difficult. But yeah, so spend a lot of time on it. Ask a bunch of questions in the discussion forums. Don't be shy about that because I guarantee a lot of you guys are going to have questions here. So we're going to do our best to get through it, and I'm going to do my best to give you guys as many examples as possible. And yeah, all right, here we go. So chapter 4, we're going to be looking at section 1 and 2, which kind of introduces you to probability, sample spaces, and events. Chapter 3, the elementary probability rules. So I'm going to be looking at the complement, the addition rule, multiplication rule, stuff like that. Conditional probabilities 4, that's kind of when it starts to get difficult. That's kind of when the wording of problems is going to kind of trip you up. Bayes' theorem is a nightmare. I mean, Bayes' theorem is really, really, really difficult. So what we're going to do is we're going to touch on Bayes' theorem. I'm going to show you how to use the formula, and then I'll leave it up to you if you would like to use Bayes' theorem when you come up to a Bayes' theorem problem. The reason I say that is because you're going to come up to a lot of these Bayes' theorem problems, and you don't actually have to use Bayes' theorem. You can use a contingency table and the other elementary rules and conditional rules of probability in order to solve that problem, where I just think Bayes' theorem is very confusing, and yeah, I just think it's less apparent than just using kind of the elementary rules. So I'll show you both ways to solve the problem that we are going to go through tonight, and I'm sure you'll probably choose to not use Bayes' theorem going forward, but you have that option. And then lastly, we'll cover counting rules. So counting rules, we kind of step away from probability a little bit, and we're going to be talking about, I guess, the independent rule of counting events, and then the rule of combinations. All right, so without any further ado, let's get into it. 4142, probability, sample spaces, and events. An experiment is any process of observation with an uncertain outcome. Okay, that's easy enough. The set of all possible outcomes for an experiment are called the sample space. Probability is a measure of the chance that an experimental outcome will occur when an experiment is carried out. And an event is a set of sample space outcomes. The probability of an event is the sum of the probabilities of the sample space outcomes that correspond to the event. Okay, so we'll give you a little bit of an example. I kind of rushed through those because I wanted to be able to write out really how to explain it. So one thing that we'll do is we'll talk about an experiment of rolling a die. So rolling a die is in and of itself the experiment. Okay, so we can kind of check off, boom, that. All right. The set of all possible outcomes for the experiment is called the sample space. So what are all the possible outcomes of rolling a die? So the outcomes we have are 1, 2, 3, 4, 5, and 6. Okay, so those are the so that would be considered the sample space. 1, 2, 3, 4, 5, and 6. Probability is a measure of the chance that an experimental outcome will occur when an experiment is carried out. So of course we know that the odds of rolling any one of these outcomes is equally likely. So I'll just put an arrow and we'll say probability of X is equal to 1/6. Okay? And then an event is a set of sample space outcomes. So rolling a die is the experiment. We roll a die. We are going to get 1 through 6. But if we wanted to test the probability of an event, say I said I'll pay you $5 if you roll higher than a 4. So then the event would be rolling higher than a 4. So the event would be rolling a 5 or 6. And so then it says the probability of the event is the sum of the probabilities of the sample space outcomes. So then we would look at each sample space outcome. So there's 5 and 6, and we'd know that the probability of 5 occurring is 1/6. The probability of 6 occurring is 1/6. We would add those together to get the probability of the event, and we would get 2/6 or 1/3, or in decimal terms 0.333333. Okay. So that's probability, sample spaces, and events in a nutshell. And that's kind of the classic example and probably the easiest example for me to give you. But that's the experiment, sample space, probability, event in a nutshell. So probability. If E is a sample space outcome, then probability of E denotes the probability that E will occur, and these conditions need to be met. This right here, all that's saying is that the probability of E needs to be between 0 and 1, okay? Such that if E can never occur, then the probability is 0. And if E is certain to occur, then the probability is 1. Okay, and then this is the other one that's important. The probabilities of a sample space. The probabilities of sample space outcomes must sum to 1. So for every occurrence, if we add all of those up, they're always going to sum to 1. So if we go back here with the rolling the dice experiment, 1, 2, 3, 4, 5, 6, we have 6 different outcomes, each of them equally likely in this case. All of them 1/6 of a chance, or 1/6 probability. We add up 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 6 times, and we get 1. So we know that the total probability is 1 in every single scenario. So this gets us to assigning probabilities to a sample space. What we just talked about was an example of the classical method. Classical method is equally likely outcomes. This is generally going to be something that occurs randomly. Like an equal weighted die, flipping a coin. Like each side is technically, or I guess theoretically, equally likely outcome. So that's the classical method. Classical method is just assigning the number of so there's the number of sample space outcomes. So for flipping a coin, it would be 2, and then just dividing the total probability of 1 divided by that number of sample space outcomes. So for a coin toss, we know that the total probability is equal to 1, and then sample space outcomes equal to 2. And so then the probability of each outcome, so heads, tails, probability of that, so I'll just put P, is going to be 1 divided by 2, or 1/2. So that's classical. Long run frequency is different. It's when we don't know the either for whatever reason, if we don't know the probability of certain events, or I guess certain sample space outcomes, we run an experiment to determine those. Excuse me. And then lastly, subjective is something that we're not really going to use much of at all in this course, but we did want to mention it. And that's just, using expertise or experience or intuition or any level of subjectivity to determine what a probability is. So an example of that would be a stock market analyst. He says that he thinks that the likelihood of a stock option going up is 70%. He's not basing it on anything, or I guess in our case, we don't think he's basing it on any hard numbers. It's his level of expertise, it's his experience in the industry, it's what he's seen before, but there's no like direct evidence to back that up. So it's an expert opinion, and that's 3. That's subjective. Finding simple probabilities. We got into this a little bit in the last slide. Sample space is finite. All sample space outcomes are equally likely. The probability of an event can be computed using the following formula, and that's just the number of sample space outcomes that correspond to an event divided by the total number of sample space outcomes. So I guess we didn't get into that one on the last slide. We got into that one on a prior slide. We got into that on this slide. So I said, what's the likelihood of rolling above a 4? So a 5 or a 6. And using this formula, the number of sample space outcomes that correspond to the event. So there's 2 sample space outcomes that correspond to the event over the total number of sample space outcomes of 6. Given that there's equally likely probability, we get 1/3 or 0.333333.